Hello, class. In this lecture, we'll finish up the topic of population ecology, which is covered in Chapter 54 in your book. First, I recommend that you look at the Not Responsible For document uploaded on the course website. This will give you the good news that you're not responsible for the final section in Chapter 54, that is 54.6. I'm also not requiring that you go through box 54.3 in that chapter, which has some sort of additional math that I don't think is completely necessary for you to go through. This is where we left off last time, considering life tables. So this is table 54.1 from your textbook. We had gone through the information that is available in this table and how this helps us to understand which age classes are contributing to the changes in the population the most. And so, for example, if we look at this last column here, we can see that most of the births in a given year for this particular age structure and fecundity relationships are for relatively young lizards, namely the 2-year-old lizards. Almost half of all of the births in this population are coming from the 2-year-olds, even though they overall, for their age, well, compared to the older lizards, have less fecundity per female, but there's just a lot more of them, as shown here in this column, where there's how many female lizards of each age are there. There are a lot more lizards that are 2-year-olds than, say, 5-year-olds, so even though 5-year-olds have a greater fecundity, they have far fewer offspring total because there's just fewer of them. So this final column here, the average births per year relative to the original females in the population, just simply means the original females that were born. And I also will remind you that some life tables are done just for a single gender. If a single gender is covered, it's usually the females because they are usually the rate limiting step in the population growth of the population. So this is just the females. So this is why it's the number of births, and specifically it's the number of female births per year for the original female. Now notice if we take all of these numbers for each age class and add them all up together, we get what is the net reproductive rate for a typical female or an average female in the population. And the numbers just happen to work out to be 1. This is not necessary. And the consequences of this number are that this population is relatively stable. It is neither increasing nor decreasing, that every female on average is generating a single replacement female sometime during her lifetime. Now let's go back and consider the first 2 columns right here. The first column is age, class, and the second column is number of survivors. If we plot this as y and this as x on an xy plot, as shown here, then we can see how the number of survivors falls off with age. The name of this kind of graph is called a survivorship curve or graph. And if we plot this particular set of numbers, then if we start at about 1,000 here, then lose half our lizards in the first year, and then slows down a bit, and then continues, so on. It sort of looks like this. Actually, should have been a bit closer to the x-axis, but anyway, you get the general gist of the shape is a concave up graph like this. In fact, linear axes are not usually used for plotting number of survivors versus age. What do I mean by that? These are the usual axes used in a survivorship curve. This is figure 54.2 from your textbook without any data being shown. So the y-axis here is age, and this is usually a linear scale. The number of survivors is usually a logarithmically scaled axis as shown here. So for example, if you look at the tick marks, instead of increasing by an arithmetic constant as one sees in a linear scale, it goes up by a constant geometric factor. So every tick mark we're multiplying by 10, 0.1 to 1 to 10 to 100 to 1,000 and so on. Okay. So this is a logarithmic scale, very different. Now the purpose of switching to a logarithmic scale like this is just simply, this then causes a straight line if there is a constant death rate for any given age. So this is a straight line on a log linear plot like this, if in fact there is a constant death rate for any age. This would mean that one's chances of surviving to the next year are completely independent of age. You're just as likely to die in the next year if you're 60 years old versus 1 year old. Now this seems kind of odd from a human perspective because this is not what our survivorship curve looks like. Let's see what it looks like for humans. This is what the survivorship curve looks like for human beings or other species that also have very high survivorship as a young. This is a characteristic for those species that have a lot of parental care of the young. So this is still a log linear plot as shown here, and if we follow along the graph here, then one sees that if one starts, say, with 1,000 individuals and follows those 1,000 individuals over time as they age, the numbers don't go down very rapidly in young age or even middle age here, but towards the end of the lifespan, there's a sudden, very sharp increase in mortality rate or a sharp decrease in survival very late in life. And this is what we do see in human beings. This seems so normal to us that it's hard to imagine something different. But in fact, many organisms have completely different survivorship curves. Take, for example, birds, one of which is shown here. In this particular case, we have a straight line. So, as mentioned before, the purpose of using a log linear plot like this is it allows one to easily eyeball differences from a straight line. So again, because we have a straight line, what do we expect? We expect a constant death rate with age. So the way to interpret this for the bird species shown here then is that a young hatchling has exactly the same probability on average as surviving the next year as a middle-aged bird or fairly elderly bird. It's exactly the same, a constant death rate. And that then leads to a straight line shown on this kind of plot. There is a third type or category of survivorship curve. This is referred to as type 3, and this is shown right here. This is the kind of survivorship curve that one sees for organisms that produce very large numbers of young or gametes. Many marine invertebrates are in this class, or many weedy species such as the dandelion shown here. They release very large numbers of seeds out into the wild, most of which don't make it. Those organisms then have a curve that looks like this, with if one starts with 1,000 seeds being produced, for example, hardly any of them make it in the first year or so, or the first fraction of the overall total lifespan. Very low survivorship at the very beginning, and then if you make it through this very dangerous stage, then you have an increased survivorship through then your old age. So a very different kind of relationship with death rate as a function of age. If we put all three types on the same graph, then we have reconstituted figure 54.2, which is in front of you right now. Let's see if you understand how to use the information here. We'll do this as a clicker question. Of course, this is a virtual clicker question because this is a recorded lecture, but let's go ahead and do this. I'll go ahead and read it, and then I recommend that you pause the video. Here is the survivorship curves that you can use for reference as you're considering this question. Imagine you have a species of fish that earlier in its evolutionary history used to be a broadcast spawner. A broadcast spawner is a fish that produces many, many eggs that then get absolutely no subsequent parental care when if in fact they are fertilized. Now later on in the evolutionary history of this particular fish, it evolved to be a mouth brooder. These are fish that hold the eggs or the fertilized eggs in the parent's mouth until they actually hatch, and then care for the young for a while. So this is an increased parental care over evolutionary time. How would you expect the survivorship curve of this species to shift during this same time period during the evolutionary change from a broadcast spawner to a mouth brooder? Would you expect this particular species to go from type 1 to type 2 or 3, from type 2 to type 1, from type 3 to type 1 or 2, or from type 2 to type 3? At this point, you should pause the recording and consider which answer you would pick. Go ahead and pick it, and then start the recording back up again. Welcome back. Hopefully you picked answer 3. This would be a classic type 3 species, and over evolutionary time then we would be expecting it to head towards type 1, so passing then to type 1 or type 2 during this evolutionary period in this history. Let's now consider population growth. We'll consider population growth first by considering the simple case of idealized simple conditions. So let's start by considering a population, a very simple population is shown here. We have 8 birds. It should make intuitive sense to you that the change in population size will be the number of births. So in this particular example, we have 1 plus any immigrants that enter the population. Looks like we've got 2. Minus the number of individuals that died, so that would be minus 1. And also how many birds left the population or immigrated. So this would be minus 2. So the overall change in population size would then be 1 plus 2 minus 1 minus 2, considering all of these different factors. So that's 3 minus 3. So overall, in this particular very simple example, we've had a change in population size of 0 by just simply adding and subtracting. Now, if we consider exponential growth, this is one very simplified process that sometimes describes what's going on in some populations. So let's consider what is meant by exponential growth in a population. First of all, as we consider exponential growth, we're going to go ahead and make it simpler for ourselves by not considering immigration or emigration, but just births and deaths. The other thing I would like you to consider is when one talks about growth in a population, one is considering a specific point in time, and so it is proper to use the word rate just to describe these changes. So we'll be considering population growth rates or exponential growth rate. So this would be then change in population size per unit time, births per unit time, and deaths per unit time. Now we need to introduce some algebraic notation so we can follow along and make connections with the equations and algebraic notation used in your book. If we consider n as defined as the total population size, then it should make sense to you at any point in time. So n is a number that can change. Then the change in population size over time can be written as delta n over t, where the Greek letter delta just refers to some kind of change. So in the example that we just covered with the birds, then this would actually be 0. For births per unit time, we'll just use a capital B, and for deaths per unit time, we'll just use a capital D. So we end up then with an overall equation. I'll write it again up here, which is just simply delta n over t. So the change in population over time is just simply equal to births in the population overall per unit time minus deaths in the population overall per unit time, measured, of course, over the same period of time. Within a population, though, one often is looking at changes in a per capita sense. Per capita just simply means per individual. Capita has the same root as head. Oh, there we are. How can we switch to per capita? Well, instead of total births per unit time, we'll consider per capita birth rate. So we'll switch then to small b, which is per capita birth rate. And so this is just simply the overall total birth rate divided by the population as a whole. Similarly, the per capita death rate will be lowercase d, and this just simply will be the overall total death rate divided by the overall population size. If we arrange these two equations then, little b equals big B over n and little d equals big D over n, we come up with another way of writing this, which is just simply capital B is small b times n, and similarly capital D is small d times n. If we substitute these in now for this equation over here in the upper left, we get delta n divided by t is equal to small bn minus small dn. Pull out the n's, and we end up with the change in population over time is just simply equal to the difference in per capita births minus deaths times the overall population size. This quantity here, small b minus small d, is a very important quantity in population ecology and is usually written as small r. So we can also write this as small r times n, where r just simply equals small b minus small d. In other words, this is the per capita rate of increase in a population is just simply equal to births minus deaths per capita, again reminding you that we were totally ignoring immigration as a simplifying factor. So to consider this might make this a little easier if one then considers actual examples. Consider a simple case of, I'll write this in this little rectangle right here. Consider a simplifying case where the number of births, let's say I'll just put if the per capita birth rate just happens to exactly equal the per capita death rate, then this means that R equals 0. It also means the change in population over time is also equal to 0 because delta n over t is just simply equal to r times the population. So regardless of how large or small the population is, if births and death rates are exactly canceling each other out, then there's no change in the population. It stays the same. So let's consider what this means then. Again, just to remind you of what the formula is for R, the per capita rate of increase. We're looking now at figure 54-4 from your textbook. The y-axis population size, or big N. This is a linear graph here, so the x-axis here is time, or it's being shown as generations. This particular graph shows how a population that in this particular example always starts at exactly the same level here will increase at a different rate depending on the magnitude of R. So if R is very, very small, meaning that the per capita birth rate is only slightly larger than the per capita death rate, the population is not going to increase very rapidly. In contrast, if we have a very large number for R, this means that the birth rate is greatly outpacing the death rate per capita, and the population size would be expected to increase far more rapidly. This should make intuitive sense to you and should maybe remind you of what you would expect with your savings with different rates of interest. And this is exactly analogous to that. In exponential growth for these graphs, R is expected or is assumed to be constant, or at least approximately constant. And in exponential growth, then one expects these J-shaped curves where the population shoots up and increases faster and faster and faster as the population size gets larger and larger and larger. Obviously, this is unsustainable. No population can exponentially and indefinitely just increase in size like this in nature. This is a kind of growth that would only be expected under certain kinds of circumstances, such as a brief period of time when there is nothing checking or slowing the growth rate of a population. Before I leave this graph, let's consider what this that in this particular case, for all of these curves, R must be greater than 0. If R, how can I say that? Well, if R was actually equal to 0, this would mean the population size was staying the same, right? So here we go. I'll draw an example of what it would look like if R was 0. If R was 0, there'd be absolutely no change in population size whatsoever with time. What would it look like if R was actually less than 0? Well, that would mean that the death rate was greater than the birth rate, and the population would be going down. It's a little hard to show this with starting at a population this small, so I'll show an example of a R less than 0 then by starting with a higher population. If we start up here, for example, this is what it might look like. Oops. Let me go back here. Okay, there we go. So this would be an example of what a population might look like if R was actually less than 0. Okay, let's do this as another virtual clicker question. The exponential growth model that we've been discussing describes the increase in population size of a population that is not constrained by resources or space, typically. That should make intuitive sense to you. Now consider this graph right here, which shows the graph of an elephant population in a particular national park, which appears to have been growing exponentially. On the y-axis here is elephant population in thousands, starting at 0 here and going up to 8,000 here. And on the x-axis here, we have years shown. And at this particular point in time, this is where the hunting of elephants was actually banned in this particular park. And the scientists then started following the elephant population numbers at this point in time, and when they plot it, they get the graph as shown like this, which appears to be exponential growth. What can you conclude from this graph, assuming that, in fact, it is exponential growth? A, none of the elephants died. B, a female elephant living around 1960 was more likely to have a baby than a female elephant living around 1920. C, the elephants adapted to the park conditions around 1955. Or D, the food available for the elephants could support more than 8,000 elephants. Looking at this graph, assuming that it is exponential growth, consider these four factors. Go ahead and pause the video and pick your favorite answer. Okay, welcome back. Hopefully, you picked D as the best answer for this particular graph, or for this particular clicker question. If, in fact, it is exponential growth rate, then there is no change in R. That is one of the, so that is why B would in fact not be the correct answer. I'll say students often pick an answer such as B, looking at a graph like this, because students incorrectly make an inference about a single female elephant by assuming that, well, if the population is increasing, increasing exponentially like this, then clearly there are more elephants being born every year, say in 1960 versus 1920, which is absolutely true, but there's also more elephants in 1960 than in 1920. And if we go back to this graph, all of which show examples of exponential growth, in all of these cases, R is constant within any of these curves. R is not changing along this curve. Compared to this curve has a different magnitude of R, but at least within this curve, R is not changing. So the relationship between the birth rate and the death rate is not changing over time. So the fact that a larger number of individuals is being added later in time than earlier in time is just simply a function of the fact that the overall population is greater, not because any given individual is suddenly having more offspring or having a higher birth rate. This is a really important concept and relates back to the difference between per capita birth rate, for example, and the overall birth rate within the population as a whole. Just because more elephants are being born doesn't mean that the birth rate per elephant has changed. And if it's, in fact, exponential growth rate, then to a first approximation, one can assume that R is constant, and which can occur if B and D, the per capita birth and death rates, are also both approximately constant, not changing in time. Okay, let's now consider a somewhat more complicated but realistic way of mathematically describing population growth, and that is referred to as the logistic growth model. This is shown in figure 54-5, which is in front of you right now. Again, population size is shown on the y-axis. So you can think of this as just simply being the familiar n. And then time is shown here on the x-axis. The typical logistic growth model, when graphed, has an S-shaped curve as shown here, where where early in the population growth, it's very rapid, and in fact looks like it's approximately exponential growth rate. So if this early part is exponential growth, as mentioned before, this is rarely sustainable, and so what one typically does see in real life is that the growth begins to slow and eventually levels off, and the population size at which it levels off has a specific name, and this is called the so-called carrying capacity of the population. Once a population reaches carrying capacity, if it is no longer changing, then what does that mean? That means that the growth of the population is now considered zero. The population is no longer changing and is now remaining constant.